Okay, so let's finish off this topic. Huh? Okay, so we talked about internal resistance just now. Okay, we talked about internal resistance. So internal resistance is bad. Any manufacturers must make the internal resistance small as possible. If not, efficiency is dropped. Okay, so yes, the flow current circuit gains electrical energy. This all we done just now. Yeah, so EMF is VR plus VR. We want V capital R to be more than the V small r. Terminal voltage must be bigger if a good manufacturer. The V small r must be as small as possible. So the V capital R is known as terminal potential. Okay, terminal potential. Okay. So remember, when you have a circuit, when you open the switch, the open circuit, the voltmeter across the terminal battery measures the EMF of the battery. Okay, remember, EMF of the battery. And open the switch, it measures the EMF of the battery. Okay. So the current, okay, this is a trick here. You see, when you open the battery, the current will flow here. Current will flow here across the voltmeter. This is the circuit. Okay. So the EMF of the battery, of course, equals to voltage across the capital R. Here, who's the capital R here? Who's having the external load resistance? The voltmeter itself. The capital R and plus the voltage of the internal resistance. Okay, this formula still works. But because voltmeter resistance is infinite or zero? Anyone? Voltmeter resistance is infinite or zero?
Infinite.
Infinite. So we assume the voltmeter resistance is infinite, the R is infinite, is infinite, infinite. So therefore, we assume that the EMF is all go to the external load, V capital R. So we assume that the internal resistance use a very minimal voltage until we can neglect. So therefore, in A level, they assume that open the switch, the reading is we can take it as EMF. Okay. Okay, in a closed circuit, the voltmeter reading across the battery terminals is less than the battery EMF. Yes, of course. Yeah. When you close the switch, voltmeter reading, now how the current going to flow? When you close the switch, the current flow this circuit. Current will flow here, this circuit. Okay. Very minimal current flows in the voltmeter. Okay. So now the current, the EMF is equal again V capital R plus V small r, but now the V capital R, the voltage across this resistance. Okay, current will flow this resistance. Current won't flow into the voltmeter technically, because there's infinite resistance. All current flow here. So therefore, in this case, the EMF, the V capital R is not as big as last time. Last time V capital R is same as EMF. Now the V capital R is not as same as EMF. Okay, because the resistance is quite not as big as voltmeter. So in this case, the voltmeter reading we call is a terminal PD. It's a terminal PD. Terminal PD. So the reading on V will be less than the EMF. Be less than the EMF. Okay, so remember, open the switch, EMF reading. Close the switch, the V capital R reading. The voltage of load will be measured. Okay. So, for example, let's say I go to the supply. So that means you have a circuit. Okay. You have a circuit and you have, okay, let's say external load R. Okay. And, okay, straight to the connection line. Okay, let's say you have a switch and the switch has been opened. You put a voltmeter here. This is how you measure your EMF. Okay, your EMF. So open the switch. Okay. Okay. But now these techniques sometimes they adapt. this technique, I won't say it sometimes. Most of the time they adopt this. Open switch is EMF. Okay, but you have to remember here. You have to remember here, because the E equals to V capital R plus V small r. This is for the voltmeter. This is for the voltmeter. Voltmeter. The switch is open now. When the switch is open, when the switch is open, the voltmeter VR is voltmeter reading. Okay. So we say E same as VR because we assume V small r is too small to 0. Okay. But sometimes in Cambridge, they do consider this value too. It's close to 0, but sometimes it's not perfectly 0. It has some value, right? V small r, although the current flows in the voltmeter, infinite, but there is some resistance here. The internal resistance takes some voltage. So sometimes they do ask like this indirectly. Okay. How do you find the EMF of the battery? 99% open the switch, the reading got is straight away the EMF. Okay, the voltmeter reading is the EMF. If the voltmeter shows 1.5, you say 1.5 volt is the EMF. Done. Just open the switch. Okay. But technically it's not correct, right? Because VR is about 0. But the proper way of doing it, 1 or 2 questions in Cambridge, they ask this. Okay, 1 or 2 Cambridge. I don't know why. They also ask this. This is the proper way. The proper way is, how do you measure the EMF correctly? Because open switch, the reading is quite close to EMF because V small r is close to 0. But how to find it correctly? So they say it like this. Okay, they say to get the switch like this. Okay, you try to have a variable resistor. You put a ammeter here, and of course, as usual, you have a switch. And they say put the voltmeter across here. Put the voltmeter across here. V is across here. Okay, so you see, you can find the EMF, the correct EMF, 100% correct, 100% is correct, no doubt about that, by using this circuit. Okay, how do you find this? Okay, we still fix E equals to V capital R plus V small r. Okay, so E equals to what? I capital R plus I small r. Okay, I small r, right? We are looking for the E. We are looking for the actual E. Okay, not like opening the switch, which is approximate value. We want to get the actual E. So they say according to this circuit, we can find the E. How many unknowns are here in this formula? We don't know the E. What else we don't know? Current, can we measure? Like ammeter, we can find the current, right? Capital R, can we measure? Yeah, the whatever resistance you put here, you can put a fixed resistance, 2 ohm or 4 ohm. We can measure the capital R. Okay, we can measure the I. We can measure the capital R. We don't know the E. We are looking for the E. Another one factor which very difficult to find, we don't know also, is the internal resistance. We don't know how much the internal resistance of the battery, newly manufactured battery, let's say. It's the newly manufactured battery. So we don't know 2 unknown. Okay, 2 unknown. So 2 unknown. What we do, we conduct this experiment. To find the E, and of course, if you want, internal resistance also can be found. Okay, so you close the switch. Find the reading of I and V. You close the switch, find the reading of I and V. Okay, I and V. So you get one reading. Then after that, what you do? You alter this resistance. Okay, resistance, increase the resistance, increase this resistance, the capital R, increase it. So get a new V and I and V value. So you get several sets. Just the manipulation is, of course, the R. The R is increased. The R increased, we get the V and new I value. Okay. Okay, now, after you got this data, I don't know how many of you have realized this. How's the V versus I graph going to look like? Anyone? Yeah. Is it a straight line with a positive gradient or a straight line with a negative gradient? I don't know how many of you have come across with this before. 1 or 2 years they asked this. Sorry. Let me. This is
What type of what graph is it?
yeah,
I versus V or V versus
V. No. We are going V versus I.
okay, V versus.
We are plotting V versus I. V is which reading? V is the voltage of the external load. This is your VR. And I is of course the current flow. Yeah. Okay, you tell me when this VR get bigger. This is actually the VR. This the V here is actually the VR. This V is actually the V of the external load, right? Okay, tell me when the VR get bigger, when VR get greater, when the external resistance increase or decrease?
Increase.
When the external resistance increase, the V capital R get bigger. Okay, good. When the capital R increases, what happened to the current?
Increases.
Goes down, it decreases, and current goes down, right? Because big
Yes.
resistance will lead to a small current, correct? So tell me, VR, when R increase, VR go up, but current going down, current going down. Do you agree?
Yes.
When the capital resistance goes up, the VR goes up, but the current goes down because the resistance builds up with more resistance. So how do you expect the graph? Is it going to be a positive gradient or a negative gradient?
Negative.
It's going to be a negative gradient. When current get big, the V are small. So you will get a straight line like this. Okay, many of you realize V versus I like it's a Ohm's law, like a going straight with a positive gradient. But this type of setup, we use a variable resistor. We put a voltmeter on top and we put a variable resistor. We want to measure the voltage across the variable resistor. You get a graph like this with a negative gradient. Okay. So now from this graph, we can find the EMF. How do you find the EMF from this graph? Okay, use your linear law. Let me rub the circuit. Okay. This first. Okay. Okay, anyone? So how do you get the EMF from this graph after you plot? So we know E equals to VR plus I small r. I put VR here. VR here, I put I small r, just for a reason. I know VR, I know VR, I know I. So can you use Y equals to mx plus C? Use your linear law. Make the VR as a subject because Y is actually your VR. Your Y is your VR. Your X is your what? Your X is your I. So rearrange this equation to Y equals to mx plus C. It's going to be VR equals to what? Negative IR plus E, correct?
Yes.
Okay, so by using Y equals to mx plus C. From this arrangement, can you find EMF? What represents the EMF? Sure, your y-intercept. Your y-intercept is your EMF. So from B versus I graph, your y-intercept is going to be your EMF. This is the proper way finding the EMF. Okay, what is your? How do you find internal resistance? Internal resistance is the gradient. The negative of the internal resistance is your gradient. So the gradient, which is your M, the M equals to what? Negative of the internal resistance. Then you get to find the internal resistance. Okay, please understand the first scenario and the second one. Both are used in Cambridge. 99% they use open the switch is the EMF. Okay, but we now realize that the V small r do have some voltage. It took some voltage, although it's quite small. The proper way of doing is by getting the circuit just now I show you. We put a variable resistor. We plot I versus V graph by changing the R. We plot V versus I. For the first time, we got a negative gradient. Okay, this intercept is going to be EMF. This is the proper way of finding the EMF. It's tedious. If a newly manufactured battery, the how to find the EMF by having that circuit and just connecting the 6S of reading, you can find the EMF. It's tedious, but you have to know both techniques. Okay, understand? So if you open the switch, they said open the switch, then you take it as EMF. Open the switch, close the switch, EMF. But sometimes if they ask you the circuit just now, they show the circuit just now, they're asking you how the V versus I graph looks like. It's going to be with a negative gradient. Where the intercept is E, your gradient is your internal resistance. Any questions so far? Can you understand my description?
Yes.
Okay, good. Okay, let me go back to the slide. Okay, so that's what I said. Open switch is the EMF, 99%. Okay, and close the switch is the terminal PD. This is not a proper way, but adapted by the Cambridge. Okay, the difference in the voltage drop across the internal resistance R is the current that is flowing through the circuit I. Then the terminal voltage is the EMF minus the EMF minus the terminal voltage is your voltage across the internal resistance. It is just an arrangement to find the internal resistance. Okay, now one example. What's the answer for the first one? A current of 0.5 ampere flows from a battery with the EMF 3 volt and internal resistance is 4 ohm. What is the terminal PD? So E equals to I capital R, I small r. Your terminal PD is voltage across the load external R plus IR. Terminal PD means B capital R. They're asking what is the voltage of capital load. So 0.5 is your I. Okay. 4 ohm is your capital R or small r? Or the internal resistance. So it's small r. Say it's small r. They're asking terminal PD. So EMF is 3 volt. EMF given is 3 volt. Okay. So yeah, use the formula. First, I think you need to use the first formula to find the current first. Then I times capital R will give you the terminal voltage. So first, understand what is meant by terminal voltage. Voltage across capital R. E minus voltage of internal resistance. Okay, so E is negative minus I small r. So 3 minus, yeah, the current is 0.5 ampere. Yes, you can get the terminal voltage, 1 volt. Okay, another one example. A battery of 1.5 volt, terminal PD is 1.25 volt. And the resistor of 25 ohm is joined to it. Calculate the current flowing in the internal resistance. Okay, what's the answer? E equals to I capital R, I small r. 1.5 is your EMF. Terminal PD is 1.25. It means your 1.25 is the entire I capital R. Okay. is joint. Okay, 1.25 volt. Oh yeah, 25 volt is 25 ohm is what? Your capital R. Your capital R. Okay, the current flowing in the internal resistance is what? I think you just use I squared IR lah, right? I capital R. You know V is 1.25. Capital R, you know 25, so you can find the current. Current in the external load and internal resistance is the same one. So what's the answer for the first one? Anyone? So V equals to IR. So V is 1.25 volt. I we don't know. Capital R is found to be 25 ohm. So you can find the I. So 1.25 over 25, which gives you how much? 0.05. Yeah, I think 0.05 ampere. Okay. Next B, the terminal PD when a resistor of 10 ohm replaces the 25 ohm. What is the terminal PD now when 25 replaces 10 ohm? So E equals to I capital R plus I small r. They're asking terminal PD. So this is your terminal PD. Looking for this, looking for I capital R. The EMF never change. So it's the same, 1.5 volt. I, we don't know the I now. We don't know the I. It's a new I. R we know it's become 10 ohm. And I we don't know. Internal resistance, just now we got internal resistance how much? You have the internal resistance, terminal PD. Okay, so internal resistance. You need to get the internal resistance. If you know internal resistance, you can find the I, then you can find the terminal PD. Anyone have internal resistance? Okay, from the first case, you can find the internal resistance already, right? 0.05 ampere, 1.5 volt, 1.25 volt. The first case, from the first case. What is the voltage used by the internal resistance? Is found to be 1.5 minus 1.25 is 0. How much? 0.25. 0.25 is the voltage used by the internal resistance. I we got 0.05 for the first case. So we can find the R. How much the internal resistance value? Anyone? 0.25 divided by 0.05 is 5 ohm. Okay. So we know small r is 5 ohm. So you put here 5 ohm. So you find the I. I is what? 1.5 divided by 15. So you'll get how much? 0.1. You get 0.1 ampere. Then you can find the terminal PD. The terminal PD is what? The terminal PD is I times R. I is found to be 0.1. And capital R is how much? Capital R, the new load is 10 ohm. It's about 1 volt. 1 volt. Okay, so any doubt about this slide? So please keep very important what is meant by terminal PD. Terminal PD means I capital R. Okay. EMF. Okay. For a battery, terminal PD can be changed or can be fixed. Terminal PD can be changed, depend to the external load. Okay. What can't be changed for a battery? For a battery, for newly manufactured battery, theoretically, the EMF cannot be changed, and the internal resistance cannot be changed. The EMF internal resistance for a battery, newly manufactured battery, is constant. Okay, remember, EMF and internal resistance is always constant. Whatever external load you applied, The current will change, but the internal resistance and the EMF does not change. Okay. Yeah, this is what we did last so far. 5 ohm, and it's 0.1 ampere. And finally become 1 volt. Okay. Okay. Your turn. Calculate the charge. Okay. One by one. Let's take a piece of paper, give a try. E equals to I capital R plus I small r. E equals to V terminal voltage plus I small r. Terminal voltage. R of 16 ohm. The current in the circuit is 0.45 ampere. The circuit is switched on for 1000 seconds. 1000 seconds, and it's found that during this time, the battery supplies 4050 joule of energy to the two resistor. Or this much of charge has been transferred. The question is the charge which the battery delivers in 1000 seconds. This is your basic knowledge. What formula do you use to calculate the first answer? The charge which the battery delivers in 1000 seconds. The battery supplies 4050 joule of energy to the two resistors. 4050 joule of energy. So what is the charge transfer? What formula? Anyone? Yeah, any formula? Current, you know.
I equals QS.
I to Q over T. You know energy.
Q equals to IT, yes.
Q equals to IT. Q equals to IT will give you the charge. Yes, good. Yeah. So I is 0.45 and the time taken is 1000 second. Yes, you get the charge. That's charge delivered. So it's 450 coulomb. Okay, part B. What is the EMF of the battery? This is, you can't use this formula, above formula. This is the definition of electromotive force. What is electromotive force defined as? The amount of other form of energy converted to electrical energy per unit charge flow. So electromotive force, the EMF is equals to the amount of work or the energy change over charge. So how much of energy has been transferred? 4050 joule of energy has been come out from the battery. For how much of charge? 450 coulomb of charge. Therefore, 4050 divided by 450 will give you the EMF of the battery. So you get 9 volt. You get 9 volt. 450 times 9. Yeah, correct. Yes, you get a 9 volt. 9 volt. So the EMF is 9 volt. Okay. So this basically never use this formula. They're using the basic definition to find the EMF. The amount of other form change to collect electrical per unit charge. So The total energy transfer is 4050 joule by the battery. The charge comes out from the battery is 450. So the amount of energy transfer per unit charge. So energy divided by the charge, you get the EMF. Any question from this slide? Okay, so we go to the next one. Third one. We have still, sorry. What is the terminal potential difference across PQ? Let me clear this. Is all ink. What is the terminal potential difference across PQ? So now you use that formula, right? Can we use that formula? E equals to VR plus I small r. We are looking for terminal potential. EMF we know is 9 volt. Do you know internal resistance? Oh, we know the R. We know the 16 ohm. So we expand it I times 16. 16 plus I times, do you know the internal resistance? We don't know the internal resistance. Oh, we know the current. The current already. Okay, good. So we no need to go for internal resistance. I capital R is enough, right? So terminal PD is V by the external load. So I times capital R. I is 0.45 and R is what? R is the external load is 16. So 16. So this gives you the terminal PD. Okay, 0.45 times 16. I think you no need to go for internal reasons. I capital R is enough. So I think you should get 7.2. Yeah, makes sense. The terminal potential is 7.2. Okay. Okay. So let's go to the next one. The fourth one. What is the internal resistance of the battery now? So I think this information can help you, right? This is your E. This is your terminal voltage. This is your I. I think you can work out your small r. E equals to VR plus I small r. So E is how much? E is 9 volt. VR is 7.2. I is 0.45. So you can find the small r. This will give you the answer for the last one. So you get 4 ohm. Okay, so you get 4 ohm, 1.8. Okay, any question from this slide? I hope you understand the working. Okay. So now, come on, class. Your turn. One minute for you.
I love you very much.
Okay. So anyone can give me the answer for the I in R? Any one of you? E equals to VR plus I small r, or E equals to I capital R plus I small r. When the switch is open, 3 volt. When the switch is closed, 2.2. If the resistor is 50 ohm, find the reading of the emitter I. When the switch is open, voltmeter is 3 volt. So this is your should be assumed as a EMF assumption lah. we assume no current, no voltage used by internal resistance. We make it as like very small. We neglect it. When the switch is closed, 2.2. So 2.2 should be your terminal PD, the VIR together. And the 50 ohm is your external resistance. So what is the reading of the ammeter? Anyone? So V equals to IR to be used. We just use the internal voltage is enough to find your current, just to find the current. So V we know is 2.2. I is how much? Are we looking for the I? R is how much? R is the external load is 50 ohm. So you get the current. Current is 2.2 divided by 50. That's your current in ampere. Okay, anyone? What's the value you got?
0.044.
0.044. Sorry. Okay, 0.04. 0.04. Something. Okay, so 2.2 divided by 50. Okay, next, the internal resistance of the battery. So how do you find the internal resistance? So you know the EMF, you know the terminal voltage now, you know the I, you can find the small r. Okay, yeah, so 3 equals to 2.2 plus I is 0.04 something, whatever you got here, and your internal resistance R. So we can work out that internal resistance. Anyone, what's the answer for internal resistance? 0.8 divided by the current you got. 3 significant figure. Yes. Okay, so anyway, I believe you can do what do you do? Just use the calculator, you can calculate small r. Okay, so this is about this topic. Okay, so we're done with this topic, but I need to add more. Okay, I go back to the Word file. Okay, so just now we did about electromotive force. We did about electromotive force. Okay, we did about electromotive force. So remember this definition for electromotive force. What is that? Okay, so remember the definition for the electromotive force. The electrical energy is the amount of other form of energy, converted to electrical energy per unit charge supply. Okay. How to measure the EMF of a source? I already told you just now in the whiteboard just now. The experiment, remember the experiment? The experiment to be used is the circuit. You can use the circuit. Okay, you can use the circuit. Circuit is like what? Battery with ammeter, with the variable resistor, with the switch, and the voltmeter is placed on top. By using this circuit and plot V versus I, the gradient will give you the EMF. Okay, so refer back to the whiteboard description I teach you. How to measure EMF of a source. To be more accurate, get this circuit and the gradient is your EMF. Okay. Then the EMF of a battery may be measured by connecting the voltmeter like this circuit. Then we found the terminal voltage is far smaller than EMF. Some is lost. Okay, now the main thing I want to recall, something which I never taught you before, is here. So you see here, the useful power. The useful power is I squared R. The power utilized by the external load is a useful power. Power useful for us. I squared small r is a waste. Okay. In exam, they will ask, what is the efficiency of the circuit? Efficiency in terms of R and small r. What is the efficiency of the circuit? So what is the efficiency formula? Useful output power over useful the input power and times 100%. Okay. Tell me what is output power here? The useful output power is actually the power utilized by the external load, I squared R. That's a useful output power. Over what is the input power of the entire circuit? The both power together is the input power. And the I squared R, capital R plus I squared small r is the total input power times 100%. This is your efficiency. So all I cancels, so you end up getting R over R plus R times 100% is the efficiency of the circuit. Sometimes in Cambridge, they just give R over R plus R as efficiency without times the 100%. Also accepted. Cambridge, they like to do that. Instead of times 100%, they never do the timing of times with 100%, just the ratio, they leave it as efficiency. So R over R plus R. I think twice, I think in past year, they asked about efficiency. What is the efficiency of the circuit? Prove that the efficiency of the circuit is R over R plus R. So this is how you need to work out 2 marks. Okay. Any questions so far? Okay. So now the last part, something new. Okay, this section. Okay, the something new is about the graph. Okay, first, power dissipation in the circuit. You know, power across the external load is I squared R, V squared R, IV. We know this. You know, learned this before. But now, tell me, look at this graph. This graph. This is a maximum power across the external load. This is the R actually, the external load resistance. This is the maximum power of the external load. Okay, you see here, you have a circuit. Let's say you have a circuit, and you have an ammeter here, and you have an external load here. Okay, like this. Okay, this is R. Okay. It has an internal resistance small r. Okay. You know, when this, let's say this capital R is maybe a light bulb. Let's say, assume it's a light bulb. Okay, let's say you raise the resistance of the light bulb. When the resistance of the light bulb raised, what happened to the current? The current definitely going to drop, right? Resistance raised, current will drop. So the power utilized by the external load is what? The power used by the external load is what? I squared R. If I use the I squared R formula. So you see, the external power, the power utilized by the light bulb, okay, it depends to these two factors. But when the resistance of the light bulb rises, the current flow in the circuit will drop. So what will happen? When, at which point, at which R, the power of the light bulb could be maximum. This is something new. At which resistance setting, the power across light bulb could achieve maximum value. Okay, this is a homework to you. Okay, through theory and through experiment, they found that, okay, the power of capital R become maximum when this is the power distributed by the external load. They say the power become maximum, it become maximum, the P become maximum, and the resistance of the external load is same as internal resistance of the battery. When that happen, let's say the internal resistance is 2 ohm, and the resistance of the light bulb, if you set for 2 ohm, then the light bulb will consume the maximum power. The light bulb will be at its most brightest, what do you call? Most brightness of light will come out. The maximum brightness will appear when the resistance of the light bulb matches the same as the internal resistance of the battery. The power dissipation across the light bulb become maximum. So this graph has been asked in exam. P versus the P of the external load versus R, how's the graph looks like? It's a curve going up and come down. And the maximum power is achieved and the resistance of the external load is same as R. Okay, through experiment has been proven, theoretically also has been proven. Okay, I can prove you theoretically. This is your homework, you can give a try. Accept this graph. Okay, accept this graph. The power has become, okay, sorry, it should be zero, not somewhere here. It should be zero, from zero. Resistance zero means no power dissipated. Okay, how to prove this? Yeah, go back to the, because we know P equals to I squared R. Okay, P equals to I squared R. Okay, so we know EMF is equals to I R plus I small r. So I is what? E over R plus R, correct? Okay, we substitute this here. So power turned to become E over R plus R squared capital R. Okay, this is the power formula. Power formula. Why I replace the I with this formula? Because I just want the equation to be only one variable. One variable is the capital R. Capital R. Because you want to plot what graph? You want to plot power versus R, capital R. So the one variable I want is R. I don't want the I to be variable also because I also changing one. So we put it in terms of E over R plus R, only got one variable. Okay, what I'm going to prove you? What I'm going to prove you? Why I'm doing this? I want to find P maximum is achieved when, what I told you, achieved when capital R is same as small r, correct? Okay, how to prove this? Okay, I believe all of you take integration, differentiation for your maths. Do you learn differentiation, integration in your Form 4 level, Form 5, I think, right? Okay, do you learn what is the use of, mainly for differentiation, what is the use of differentiation, dy dx? There are lots of uses of dy dx. One of the use is to find the gradient. Another one of use, the one focus here, is to find the maximum or minimum value. Do you remember still?
Yes.
dy dx is used to find a maximum or a minimum value of a quantity. So we're going to use differentiation. So we do dp dr. We do what? dp dr. dp dr. When P become maximum, dpdr will attain how much, what value? When
Zero.
P, that's very good. When P is max, dpdr must attain 0. You must equate with 0. So what you do, this, I believe your maths is strong. This is your P and R formula. You do dpdr. Takes this as U. Okay, you expand first, better. Expand it. So E squared R over R plus R squared. You put it, expand it, expansion form. Still it P. Okay, take the upper one as U and down one as V. I don't know. This is how you use to find dy dx, right? Dy dx, what do you do? Dy dx is, if it's a fraction, use what? v du dx minus u dv dx, right? Over what? I forgot. Totally forgot this. V du dx minus u dv dx over what? V squared. V squared or 2v? Can't remember. Okay, you recall back. Okay, you put this as u, this as v. You put into this formula. You do differentiate, get the dpdr formula. Then you equate with zero. You will get r equals to small r. Give a try. Give a try as your homework. Okay. So P maximum achieved when dpdr is zero. When dpdr is zero, the equation you will get r equals to small r. So conclusion, this you can theoretically is proven. You can give a try. This not asked in physics exam, but how to prove it. So conclusion is, you must know is P become maximum when external resistance is equals to the internal resistance. This you can give a try. I forgot down here. It's to you. What is that? You give a try and you get this conclusion. Any question from this slide? Any part you don't understand? Okay, class. So I leave it with the homework for you. Mathematical working. Prove, derive this, get the dpdr, make dpdr 0. Okay, so you will get r, capital R equals to small r. So P max achieved and r, capital R equals to small r. So in exam, this is for fun now, we are deriving. But for physics purpose, you must understand this. Power become maximum and capital R equals to small r. This is something new now, they will ask in exam. Okay. So any questions so far? This is about this topic. Okay. So what you learn finally? Okay, you learn about current, resistance, potential difference, EMF, internal resistance, and finally efficiency, and how when causes P become maximum. That's about this topic. Okay. Next class, another one class, we'll be doing the questions. As homework, give a try with the. Please give a try with the past year. Okay, tomorrow we'll be discussing the past year. Okay. Any questions? Okay, so if you don't have questions, I stop here. I see you tomorrow. Okay, before tomorrow, please send the graph you plotted. Maybe some of you haven't done. I only received one. I want you all of you to send so that I can give a comment tomorrow. I won't show you the name, just the graph I will explain. Okay. Okay, thanks.